CPV efficiency is slightly different because of its nature, the nature of the technology. And we have a three-stage process in terms of the losses of energy. First, we lose in the primary reflection. Secondly, we lose in the secondary reflection. And then there is a loss, set of losses in the PV cell itself. In the left picture, we see a mirror, a dish mirror. It has its own natural loss. Not 100% of the light is reflected into the secondary mirror. Some light is being absorbed by the mirror. Some light is not being reflected to the secondary mirror. We lose it. It reflects back out. So just because we have a dish and a mirror, which is a mirror, a very thin mirror, we lose it right there. By the way, the thickness of the mirror itself is several microns. The reason it's several microns is because I would like to have as least amount of metallic material in the primary dish, because I want the least amount of I want to reduce the temperature. I want to keep the temperature down. So I use the least amount of metal. More metal, it will get hotter. And again, higher temperature, higher losses, bigger losses. The idea is to have a thin layer of mirror on the dish, not to let heat being generated. So the primary reflection is number one loss. Secondary reflection has the same idea. Concentrated light is being injected into the secondary mirror, which get hot because it's focused, it's concentrated, it's high density of energy. Mirror by itself, by its nature, has its own losses, but the secondary has a higher temperature. So we have a loss right there. And then this concentrated light is being injected into the PV cell itself, and as we've seen before, it has its own set of losses. So CPV is a little bit more complicated in terms of losses just by its nature. But as we've seen before, its total efficiency is much, much higher than the classical PV cells, the flat ones. Because bigger area of light is being focused into a small area of light, converted to electricity using small area. So within a given area, I can get more output power of a system. Let's look at the CPV efficiency, kind of a roadmap between 2007 and 2020. We'll see where it goes to. The upper graph, the light blue one, is a cell efficiency, basically a world record. We can see that it starts from 40%, goes up to 50% in the year 2020, according to research trend. The red graph is a CPV cell efficiency and more commercially available systems on a cell level. It starts from 35, goes up to about 45. Still on a cell level. If we go to a module level on the green, we see that it actually starts from 21, goes up to 40. Module level has more losses. Temperature, mechanical, electrical, environmental. So module level will be less than cell level. Now a CPV system level on the dark blue graph will have even lower. Starts from 19%, goes up to 35%. Still much better than polycrystalline and monocrystalline and thin film technologies. Cost more, but higher, much higher efficiency. This chart, this list of cell efficiency in a concentrated, should give us kind of a picture of where we stand in terms of what we lose in each stage. We start with ideal 100% performance solar resource, 100%. The first reflection loss will bring us down to 96%. The second one, the optics for that, meaning the ability to concentrate the light beams into the secondary mirror, we lose another 5%, will bring us down, another 3% will bring us down to 93%. Remember, we started with 100 already. Before we did so much, we are already losing 7%. Secondary reflection loss, another 4%. So actually, before we hit the cell itself, just because of the secondary reflection loss, we're losing another 4%, going down to 89 already. The optic of the secondary optics, the ability to concentrate that light again into the prism, the optical prism, we lose another 5%. Now we start talking about the cell itself. That the illumination of the cell itself will reduce it another 2%, we're 82. Cell temperature, 7% we lose because of the cell temperature. So we are down to 75% efficiency right there. And again, because the spectrum is not the complete full spectrum, it's only the visible plus minus, we're losing another 2%, so we're down to 73. And the cell stringing brings another 5%. And the last two ones is more electrical and mechanical, more kind of system level cell efficiency reduction. The resistance of the wiring and tracker misalignment. Because the reason we go to concentrated PV system is because we want in a smaller area altogether to generate maximum electrical power. And in order to make even further use of that CPV, we will mount it on a tracker. We spoke before in previous session about tracking system in general. We will have a very detailed tracking systems session, and in particular about CPV. But because I have a tracker, and tracker is an electromechanical system, it has misalignments. 4% I lose only on that misalignment before it goes out to the grid. So the accumulated losses are 36%, starting with 100, ending with 64. But still, the efficiency is twice as much of the CPV as a whole. So if you balance it out, it's much more cost effective to have a CPV, especially when we have limited area to play with.